Good afternoon, everyone. So I think we'll get started. So it's a great pleasure to welcome Professor Xiaodong Xu from University of Washington. Xiaodong is a Boeing Professor of Physics and Professor of Material Science and Engineering at UW. He got his undergraduate degree from the University of Science and Technology of China, and then got his PhD from University of Michigan, and following a postdoc at Cornell, joined UW. So Professor Xu is a leading experimentalist in condensed matter physics. He has his work has had major impact on two-dimensional quantum materials, seminal contributions to spin and Valley physics, exciton and Morel phenomenon, and most recently, he's widely recognized for the breakthrough experimental observation of fractional quantum anomalous Hall effect, which I assume we are going to hear about today. So please take it away.
Thank you. Thanks for the invitation to come to Yale. I hope you can hear me well, right? Yeah? Okay, good. Yeah. So actually, even though if you look at my CV, I have nothing to do with Yale physics department, but I consider myself part of Yale physics. My postdoc advisor is Palmer Kuhn. He got a PhD degree here. Okay, so I'm part of you. Yeah. At least I claim it. So today I'm going to tell you something I'm excited about is how we can use photons, right, light, to probe these low energy excitation like fractional charges. So the system I talk to you today, right, is actually belong to the broad condensed matter physics. But if we look at the condensed matter physics, it actually has tightly connect to the development of technologies, right? Here's one example I really like, right? Back to 1948, the three gentlemen in Bell Lab, right? They developed these germanium point contact, which is the beginning of transistors. And we know that the discovery of a transistor really revolutionized these microelectronic industries, right? From these vacuum tubes now to these iPhones, everything we have. And here are still these roadmap from TSMC, right? Describe how the transistor evolves in the last decade, right? From these 20 nanometer scale to the 2 nanometer we have today, and they continue evolving. Okay. So during this development of these transistors, actually there's something amazing happened in condensed matter physics. So that happened at the end of 1970s. So people are focused on these silicon field effect transistors. And with these silicon field effect transistors, they provide a high quality 2D electron gas systems. So what von Clinton found is that if you apply a vertical magnetic field perpendicular to these 2D electron gas, then pass a current in these longitudinal directions, what he found is that the Hall conductance actually quantized in an integer value, right, in the units of E squared of H. So if you measure the Hall resistance, you will see these plateau features. Okay, so that's now we know these as a quantum Hall effect. And the quantization is integer, okay, with C is a chain number. And a couple years later, right, the material actually developed. Now it's gallium arsenide field effect transistor. It's an even higher mobility 2D electron gas. So in such a high mobility 2D gas systems, the electron-electron interaction becomes important. And what all these physicists found out is that in a partial filling of these Landau levels, right, the strong interactions actually open up a quasi-particle gap. Now the plateaus, right, these quantization actually can go to these fractional numbers of these E squared of H. So now we know this is a fraction quantized Hall conductance or fractional quantum Hall effect. So what the Bob Laughlin, right, found have this beautiful theory, right, explain these fraction quantum Hall effect is a charge basically, right, has fractionalized values. It's intrinsic wave function properties. Okay, we know it's a fraction quantum Hall effect. So this is an interesting phenomenon. And this phenomenon itself also lead to another kind of interesting excitations called anyons. So anyon, right, in a nutshell, right, it's considered as a kind of strange particles in a two-dimensional systems. So if we just consider two particles, right, identical at the two different positions R1 and R2, then we can simplify this wave function, right, just psi with R1 and R2. Now we start to exchange these two particles, exchange their positions. Then the wave function, right, initial wave function and the end wave function can be connected by these phase term e to the I theta. And with theta can be different values. For example, if theta is 0, we know it's a boson, and the theta equal to pi, right, it's famous when we know fermions. And what this mathematician actually shows that is that the theta actually can be a rational fractional value of a pi. And Frank Wilczek gave this name of anyons. So initially, anyon was an abstract concept, but the discovery of a fractional quantum Hall effect gave rise to a physical system actually to realize this abstract concept. So, right, Bert Hopling and also Frank Wilczek, right, they theoretically prove that these fractional quantum Hall effect excitations actually are anyons. They follow these statistical exchange, right? These fractional statistics of the basically it's a signature of anyons. So initially, right? There's you know the sample mobility is limited, and then it's all the fractional quantum states has these order denominator. But later on, there's also even denominator states discovered. This motivate the community actually come up new ideas, right? This is a paper from Nicholas Reid, and they show that there's a non-abelian excitations, right, in such a systems. Okay, this becomes really important concept because these non-abelian excitations now we know can use to build these fault-tolerant quantum computations, right? The concept was established by Katev, right? Shows that basically this paper proved that how you can use non-abelian anyon, right, to build a fault-tolerant quantum computers. The key idea is the metabolic wave functions highly degenerate, and they're immune to local perturbations. So that's sort of the main source of the quantum decoherence. So then how we can realize these non-abelian anyons, right? There's many different ways. One is to engineer even denominator fractional quantum Hall states, such as 5-half states. Now we know as more rate, right, 5-ion state, for example. The other way is that you can interface a superconductor with fractional quantized Hall edge states. And in this case, right, you can realize these power fermions, which is fractionalized Majorana fermions. The scheme is there, but actually it's quite challenging to do. So here I just use example, right, done by Philip King at Harvard. They interface these niobium nitride superconductors with a monolayer graphene, but in the fractional quantum Hall regimes. And so they see these Andreev reflections, right, cross Andreev reflections across these superconductors, but there's no non-abelian anyon has been observed yet. So this is the reasons, right? And the reason is that, first of all, right, this fractional quantum Hall effect actually has low energy excitations. It's fragile. You need hundreds of millikelvin temperature. And if you talk about non-abelian anyons, right, the excitation energy even smaller. So technologically, it's difficult to do. The second is that the formation of this fractional quantum Hall effect requires high magnetic fields, and we know that the superconductor, right, doesn't like a magnetic field. Even though we have a superconductor, for example, has a high critical field, but once you apply magnetic field, you can form a vortex. And the formation of a vortex actually just kill these non-abelian anyon excitations. So the solution, right, is that to find a fractional quantum Hall effect, but at the zero magnetic field. So we now know as a fractional quantum anomalous Hall effect. The word anomalous means we don't need a magnetic field to do this. So the concept of this fractional quantum Hall as zero magnetic field has been there for a long time, actually. So now, for example, right, even back to 1989, Bob Laughlin already considered a case that you have a spin lattice system, for example, right? He considered there's a fractional quantum Hall effect in a spin lattice. And also Nick Reed also considered fractional quantum Hall effect in periodical potentials, for example, as the development of this AMO system, right, early 2000s. Then the community has been thinking about how you can realize these fractional quantum Hall plus these optical lattice systems. Basically, it's quantum simulations. So that's been going on. But all these platforms, right, they still require a magnetic field to break the time reversal symmetries. And the concept of these zero magnetic field fractional quantum Hall actually was firmly established back to 2011. There's a number of theory work, right, to calculate this. So either do modeling, so do these numerical calculation to calculate the many body chain numbers. So all these models has a slightly different flavors, but they point out a key concept, which is that we need a flat chain band to realize these zero magnetic field fractional quantum Hall effect. Right? What the flat chain band offers is the three key ingredients. The first one is it's a chain band, right? Means you have a topologies. Okay, the band must be topological. The second one is it's a flat band. That means it will give rise to these strong electron-electron interactions. We know it's also important, right, for fractional quantum Hall. The last one is that the system also need to break spontaneous time reversal symmetry breakings, so such as ferromagnetism. So this can come from strong interaction effect. So even now we know that right, how we can realize such a system, basically to create a flat chain band. But it also is difficult to do, right? There's a lot of material systems, and how do we know which system can realize such effect? And we don't know how flat is flat. So there's a lot of unknowns. And the method we use is to use these Mori materials. I think all of you know what the Mori material is, right? Basically, you have two-dimensional materials, and you stack on top of each other. Either these two materials have different lattice constant, or you can just have other trace angles. Right? You can have these interference pattern with these two crystals. They form these Mori superlattice patterns. The concept has been there actually also more than a decade, right? There's a lot of the early work already done at the late 2000 actually, right? For example, like Iva Andres' group already showed they studied these Van Hove singularities in these twisted graphene that was grown by these epitextual growth, for example. But I think the breakthrough really comes from these two works, right? The first one is the theoretical work by Allen, shows that there's a match angle in twisted homobilayer graphene, which shows the flat bands. The second, I think, really motivate the field is that the work from Pablos at MIT, right? They observe these unconventional superconductivities in match angle graphene. So that really shows that once you have these Mori materials, we have an opportunity to engineer flat band. The other key concept is we need topologies, right? So what we found is that in these twisted MO-T2 bilayer, actually the host a flat chain band, and with such a flat chain band, we observe these fractional quantum anomalous Hall effect. I'm going to go into detail, talk to you all these results and some others. What's exciting is that right, these fractional quantum Hall actually it's a topological physics. What that means is it should not be material dependent. You should be able to observe in different physical systems. And indeed, right, there's a second system now to observe these fractional quantum anomalous Hall effect. Right, it's the rhombohedral graphene pioneered by the group of Longzhi in MIT. So these two systems are quite similar, but with a subtle difference. For graphenes, it's a semi-metal. So what the semi-metal means is right, it's easy to make a contact. So once you have a good contact, you can observe, for example, it's fractional states at the small fillings, right, below 1/2. So these low filling states is difficult to do for our semiconducting systems. Okay, so we in the transport, we actually don't observe these low filling states. We can use different techniques, but not in transport. The semiconductor has its own advantage, right? Because the semiconductor, so the screening actually is weaker compared to graphenes. So interaction is stronger. So what it means is that the energy scale of these many body states is about order of magnitude larger than in graphene. This is important because eventually, right, if we're going to engineer these non-bilayer anyons, and these large interaction strengths become important, right? Because we want to see it experimentally, and then the energy scale need to be large. The second important thing I'm going to emphasize today with the main part of my talk is that it's a semiconductor has a very strong light and matter interactions. So this offers opportunity, we can use light to probe these fractional states. Okay. So my talk can just focus on these twisted MOT2 bilayers. So let me just briefly introduce you the material system. What we work is in a class of a transition metal dicotyledons. If you look from the top, right, that's the crystal structure of a monolayer TMDs. Has these hexagonal lattice structure, and these the corners, right? One is with collagen, the other is metal. So the inversion symmetry actually automatically breaks. The broken inversion symmetry will lead to these we call valley contrasting properties. So here I show you the momentum space of this monolayer TMD, right? We have these 6 Dirac cones at the corner of Brillouin zones. It's a semiconductor, so that we have a band gap, right, at the corner of Brillouin zones. What's important is that for individual values, such as k and then minus k, we have a non-vanishing valley moment, and the resulting is distinct optical selection rules. So for k valley, right, coupled to sigma plus polarized light, and the minus k actually coupled to sigma minus polarized light. Okay. What we do is we stack these monolayer TMD on top of another one, right, and form these with little twist angle. Then we form these homo bilayer, right, Mori superlattice. And within these single unit cells, there's a 2 high symmetry point, as I highlight here, but 2 different colors. Right, one high symmetry point we call B, which is a metal on top of collagens. Okay, so metal on top. You can think of it it's a pseudo spin, right, with pointing up. And then the other, right, C, we can think collagen on top of metal, and then you can think of a pseudo spin pointing down. Now we have these 2 pseudo spins. They're energy degenerate, and form these honeycomb lattice. Okay. And my collaborator, right, my colleague Matt Yanko, is actually now able to image these layer pseudo spins using STM. So here's a topographic image of STM of 2.7 degree twisted samples. And you can see that there's these high symmetry points, right, with MX, XM. Those are 2 domains, layer pseudo spin I talked to. Then he also imaged the denser states from these flat bands, and really shows that the denser states are localized at these MX and XM point. Okay. The reason we studied this system because Allen has these seminal paper shows that in twisted TMDs there's a flat chain band. Okay. So then what he shows that in the single particle pictures, the system can be modeled as a quantum spin Hall insulator. Right? It's protected by transversal symmetries. What's really important, he shows that this layer pseudo spin actually forms skirmions. Okay? And these skirmions actually give rise to real space topologies. And we can look into a bit more details, right? Why these layer pseudo spin skirmions give rise to this topology. This pointed out by my collaborator Wang Yao at the Hong Kong universities. So we know that, right, we can look at the electrons' equation motions in the real space. Here, right? The first equation consider the positions, and the second consider the crystal momentums. So if we look at the first equation, on the right, the second part is k dot cross omega k. So here, right, k is the crystal momentums, and the second is a Berry curvature in the momentum space. So this Berry curvature in the momentum space considered as a pseudo-magnetic field will give rise to this valley Hall effect. Then we look at the second equations. The second equation, the first one is r dot, which is the velocity v, right? And the second is omega r, is a Berry curvature in the real space. Then you can consider is velocity times a pseudo-magnetic field. If we just apply a real magnetic field in the system, right? We know v cross b is a Lorentz force, will give rise to Hall effect. But in this case, we don't have a magnetic field. What we have is real space Berry curvatures, omega r, which is written down by this equation here. It's the derivative of these wave function of the position r. So if I give you a homogeneous crystals, then these derivative of u to r actually vanishes. What it means is that just give you a single crystal line. There's no this barrier curvature effect in the real space. But the situation changed in this Mori sublattice, right? In the Mori sublattice, as I show you here, as you go from this layer pseudo-spin, say, pointing up to the layer pseudo-spin pointing down in the real space, the pseudo-spin must rotate, right, in the real space from these pseudo-spin skyrmions, as Alan pointed out. Then imagine you electrons and go through these pseudo-spin in the real space. You go through these skyrmions, then we must pick up these pseudo-magnetic phase. What it means is, well, now we have these the layer pseudo-spin textures give rise these barrier curvature in the real space, and give rise these barrier curvature in the real space. Then will give rise these anomalous Hall velocities. So that's where these topology coming from. And this becomes important because the topology is coming from this real space, these layer pseudo-spin skyrmions. The other way you think about it is as long as you make a Mori sublattice, right? And you have these Mori pseudo-spin skyrmions. Then what it means is we don't need a magic angle to do this, right? And this picture, because it already holds. So coming to detail is that you can realize such effect in a large range of trace angles, as long as the bandwidth is small. So there's a phase space for this to happen. Okay, I'm going to show you a bit more, emphasize a bit more later. So the first thing is, now we have the system twist MOT2. The first thing is want to demonstrate is broken time-reversal symmetry. Yeah.
Could you maybe just restate this slide? So I just want to talk about time-reversal symmetry. So before you, if there is no phase transition, so it's just single particle picture.
Yes, these are all single particles. Exactly. So that's exactly what I'm talking about. Now we need to talk about the interaction induced the time-reversal symmetry breaking.
Right, but on the previous slide, it already sounded like we have time-reversal symmetry breaking.
No, it doesn't break. So what's happening here is this is only talk about one valley. There's another valleys.
So basically, yeah.
It's a quantum spin Hall.
Yeah. So again, we consider the same energies that are more than one valley. At a single energy, there is more than single band.
That's right.
Values, right?
Exactly. Yeah.
Together they preserve.
Exactly. Your understanding is 100% correct. Right. So everything we talk about here, that's why I say it's a pseudo-magnetic field. It doesn't really break time-reversal symmetry. We're talking about valleys. Now you have a second valley, and then the time-reversal symmetry holds for the whole system. That's the picture where this topology coming from gives you quantum spin Hall effect, which is a single particle and the system protected by time-reversal symmetry. The next thing, exactly the question, what do we need to do, right? We need to find the time-reversal symmetry breaking. That's what I'm going to show you. So now I have a quantum spin Hall. Quantum spin Hall basically is two copies of a Xiaodong model, right? With one spin copy up, the other copy down, the energy degenerate. That's exactly what you mean. Then what we need to do is hopefully, right, the system has a strong interactions and they give rise these spontaneous ferromagnetism. Then we'll break the spin degeneracies, then lift the two copies. These will give rise a Xiaodong model, basically. So let me just introduce you the experiments, right? The cartoon right here shows the sample we have. I have a twisted MOT2 bilayers, and with a dual gated structure. We have a top gate and a bottom gate. And these two gates actually can control the carrier density in the sample. We can also control the sign of these two gates and give rise an electric field across these bilayers. So in the measurement, what we use is called magnetic circuit dichroism. So we measure the optical absorption difference between left and the right circular polarized light. So you can think of it as a measurement of Hall conductivity by the optical frequencies. And also define a filling number mu here. The filling number mu means number of carriers per Mori unit cells. So when the filling number, for example, -1 means there's a one hole per Mori unit cells. If it's a fraction number, it means that means there's a fraction number of holes per Mori unit cells. Okay, so what I show you, the data I show you here is the measurement of a circular diagram as function of an electric field in its vertical axis across a sample, and the horizontal axis is the filling numbers, right? Means the carriers per more unit cells. And the color scale here, if you see a red color, means there's a non-vanishing MCD signal. It's an indication of ferromagnetism. So now you can see that within a large phase space of electric field and filling number, right? We have a phase space of a non-vanishing MCD signal. That's indication of my ferromagnetism. Okay, right? So this ferromagnetism is purely coming from the carrier-carrier interaction. It's a stoner type of ferromagnetism. Within this phase map, I can already see something interesting, right? This fractional filling, for example, 2/3, right? We see that there's a little, kink features. Already indicates there's a state underneath this ferromagnetism. So usually when you see a circular diagram, right, it's an indication of ferromagnetism, but it doesn't prove it's a ferromagnetism. For example, we know sugar molecules can also give you circular diagram, right? But sugar molecule is not a ferromagnet. So to prove you have a ferromagnetism, you have to measure the magnetic field dependence, show the hysteresis effect. Okay, that's exactly what we did. So here I show you a few different curves. We measure these circular diagram, right, as function of magnetic field and swing forward and backward, right, in this horizontal axis. And each plot here, right, each panel is taking the different filling factors, right? The top is filling factor -1, for example, the green as a 2/3. So you can see that there's a pronounced hysteresis, right, for each filling factor. That's really demonstrated. We do have a spontaneous ferromagnetism, break the time reversal symmetries. Then we can also just plot the hysterical component only, okay? And as function of a doping, as I show here, the vertical axis now is magnetic field. So this plot is basically showing that how the cohesive field changes, right, as function of dopings. Now you can see the cohesive field is dramatically enhanced at the integer filling -1, and also enhanced at the fractional filling 2/3, and also a little bit filling at the -2/5, etc. Now we all know that this -1 is quantum anomalous Hall state, 2/3, 2/5 two fractional quantum anomalous Hall state. Okay, so what I show you is basically saying that the system, first of all, has a spontaneous time reversal symmetry breaking. The second is we can just use very simple optical measurements to actually know that there is a fractional state in existence. But just by looking at the data itself, you don't know they are fractional quantities, right? To prove that, we have to do transport. Okay. So doing transport is actually quite challenging for such a sample because it's difficult to make a metal contact to a couple layer of semiconductors. And my group actually not specialized doing this, but somehow we did it. So the students are really fantastic. I want to just walk you through, the key results, right? So first of all, we to make a good metal contact. So for each contact, we pattern a local gate on top of them. Okay, so it's like basically for each contact, we have this individual servant, right? To dope the contact areas. So we can dope the sample and then to make a good contact. The second thing we did is for every steps, we do these AFM cleaning, okay? So you can see that, right? We basically, this AFM cleaning usually takes about 10 hours. It's a this movie, but it takes more than 10 hours. This process actually can clean the surface, okay? And the end results, right? Initially, you see a lot of bubbles on the surface, but once we do the cleaning, the device looks quite smooth. So that's how we make a good contact and make a good device. And if everything works well, this device will, it takes about 200 to 300 hours to make one device like this. But that was the lucky case. Usually, something gonna happen. So what my students do is they usually make 3 or 4 devices together, and hopefully after a month they will get one device. Yeah. That was it's already a lucky case. All right, so let me show you the latest data we have. Right, what I show you here is a transport measurements at the temperature 100 millikelvin. And horizontal axis is the filling number, and the vertical axis is the resistance. And this blue curve is anomalous Hall measurements, and the red curve is measurement of RxX. So there's a few regions of interest, right? The first is the filling number -1. We see the Hall resistance is quantized, right, in a unit of h of v squares, and with vanishing RxX. So that's the quantum anomalous Hall effect. Then as we increase, reduce the doping in this case, right, you see that RxX will drop first. Sorry, RxY will drop first, and with increased RxX. And this regime we call anomalous Hall metal. So what it means is that it's a ferromagnetic metal phase, but with partial filling of a flat chain band. And then we keep doping, right, match these 2/3 fillings. Now we have a vanished RxX again with RxY quantized as 3/2 of h squares. So that's my 2/3, right, FCI state. And as we continue goes, you will see that the RxX increase with drop RxY. Then eventually, then quantize again, right, at the 5/3, and we have another one which is, basically we have a 3/5 state, and also another dip at the 4/7, etc. And this small filling state is not fully developed, partially due to a small gap, partially due to the bad contacts, actually. Yeah. Okay, so at least we observe a Jain sequence of these FCI states. And we can also just measure these RxY as function of a magnetic field, as I show here, right? The blue curve is RxY, the horizontal axis by sweeping the magnetic field forward and backward. We can clearly see that the RxY is quantized at the zero magnetic field, right? And with vanished RxX. So that's this demonstration of this fraction quantum anomalous Hall effect. And what's nice about the system is that it's highly tunable. So what I show you here is a phase diagram, right, represented by a measurement of RxX. The vertical axis is electric field, and the horizontal axis is filling numbers. And the color scale here, the blue color represents vanishing RxX, and the red or dark color represents very large RxX. So with this phase map, you can see that we have this quantum anomalous Hall state at the integer filling -1. And we have these fraction quantum anomalous Hall states at the fractional fillings, and then near -1/2, we have a finite RxX, but with quantized, not quantized, with RxY at the 2h of v squared. So that's actually a composite thermal liquid state, but at the zero magnetic field. Okay. So there's a lot of things happening. And also you can see that as we tune this electric field, right, there's a lot of phase transition happens. Okay. Because, evidenced by these change of colors. So for example, let's just focus on these 2/3 state. And the blue color represents these RxY, and the red is RxX, horizontal is electric field. So the data is taken at the 2/3 filling. So initially at the small electric field, right, you see RxX vanishes with quantized RxY. That's my 2/3 FCI state. As I increase each electric field, now you will see that these RxX will increase dramatically, right? Change from 0 to about a few hundred kiloohms. Then with RxY actually nearly vanish. Okay, so that represents a charge ordered state, likely to be a generalized Wigner crystal state. And at the larger electric field, then RxX drops again with the vanish RxY. So that's some kind of metallic state. So this shows you that we can actually tune this electric field to realize these topological phase transitions from this FCI state to some kind of a charge order, but the topological trivial state. The other nice thing about system, as I mentioned to the beginning, has a large energy gap. So what I show you here is a measurement of RxX as function temperature, right? This vertical axis is temperature, horizontal is the filling number. The data is taken, right, focus on these fractional fillings. The blue color represents the vanishing RxX. So just by looking at this data, you will see that, for example, right, this -2/3 state, you will see that the dip of this RxX can survive to pretty high temperature. When I say high, it's 2 to 3 Kelvin. It's already high if you know about the fraction quantum Hall states. Okay, and this data is taken at the zero magnetic field. That already tells you the system has a large energy gap. So if we do thermal activation measurements, it will tell us the gap itself is about 20 Kelvin. Okay. All right. Last thing is about twist angle dependence. As I mentioned to you at the beginning, right, the effect can be seen with a wide range of twist angle. We have been seeing this effect from twist angle about 2 degrees all the way to about 4 degrees. So what I show you here is quantum anomalous Hall measurements, right, for the twist angle from 3.1 to about 3.9 degrees. Right? In the middle panel is measurement over RxX, and the bottom panel is measurement of RxY. You can put, there's some kind of detail difference, but the main feature, right, vanishing RxX with quantized RxY always preserved at this zero field. So this tells you we don't need a match angle. The effect can be seen in large trace angle, at least because the topology is coming from these layer pseudo-spin skirmiones.
Just to get on the same page, so we're talking about filling factor. Okay, it's not a conventional filling factor for the magnetic field at 1 dollar.
That's correct.
It's filling factor of a band, I guess.
Yes, exactly.
Just can you tell how you count mu? So I mean, you have degenerate bands. So for example, nu equals -1 corresponds to what? To fully polarized.
Yeah, it's a filling factor 1. Basically, it's a top of valence band is field Maury band. We're talking about Maury band. Yeah.
Right.
Yeah.
But you have more than one band, right? So there.
It's a spinning valley polarized, right? So basically, it's isolated one band.
And very polarized.
Yes. Yes.
Okay. So nu equals 1 corresponds to 1 fully spin and very polarized.
That's right. Exactly. Yeah.
Okay.
2/3 means a fractional field.
All right.
Yeah.
And then now the fraction, so say 2/3 is what is again it's one band.
One band, but the 2/3 field. Yeah.
Okay.
Yeah.
So also fully polarized.
That's right.
Fully spin polarized.
That's correct. Yeah.
Okay. Okay.
Yeah. So that's how we count in the filling. You can think of it just like atomic unit cell band. It's the same as a block band. You know, one means full field.
Yeah. But
yeah.
So nu equals 2 correspond just to a fully occupied single band that's spin up and spin down.
That's right. Exactly.
And then you should see nothing.
That's exactly right. We have we're going to talk about 5 o'clock. I can show you some data there. Yeah.
Okay.
Yeah. What you're saying is exactly correct. But it's not that simple. There's a lot of interesting physics there as well. Yeah.
Okay. Yeah. Just to understand.
That's correct. Yeah. What you're saying is correct. So this will be repeated, right? You know, means one, right? Filling factor 1 means one spin valley polarized band is completely filled. Yeah. That's what 1 means.
And you control mu by not by magnetic field, by the displacement field, right? So by D. You control filling.
We can control it by D as well. Yes. But the thing is, when you control D, right, is you really change the Hamiltonian itself. So what that means is
how do you control mu?
Doping. So 2 gates. So I have 2 gates. Yeah. So I can tune a gate.
Okay, it's not D, but okay. So it's sum of the voltages rather than the difference of the voltages.
Exactly. So what I do here, if you want to just change the doping, you keep 2 gates the same, but tune them together.
Gate doping.
So So let's go back to this plot. So basically, what we do is we fix this D equal to 0, and I just tune the doping here in this axis. So that's why I have this 2-dimensional phase diagram. Yeah. Right. Okay, now I introduce you the basic picture, right? We have this twist demo T2, and it can host this fraction quantum anomalous effect. And we know that, right? Just like fraction quantum Hall, the system is supposed to have, it should be any excitations with fractional charge. But expectation is expectations as an exponent, right? We need to see it. And the question is, how can we see the fractional charge excitation in this new system? So I'm going to show you that we can do it with optical measurements. So, but let's just look at the historical, right? How is the fractional charge measured in this 2-DAC system in the fraction quantum Hall? Even though, right, Bob Laughlin predicts these fraction quantum Hall excitations, fractional charges, but it takes the community actually about 20 years, right, to really establish. So the convincing measurements is from these Marty Habermas group at the Weizmann Institute, right? They do these short noise measurements. So basically, what they compare these short noise measurements of these 1D Carroll edge channels with these the theoretical calculated noise from these 1D large integer liquid. What they found is that the measurement should be described the fractional charge excitations. So that's kind of a convincing evidence in the community. But there are some other measurements, right? You can create the anti-dots to these resonant tunneling measurements, and from these tunneling spectroscopy, you can infer the fractional charge excitations. So there's also measurements from Amir Yacobi, where you use these scanning electron transistors to measure these energy level near a charge defect. So here's beautiful results, right? For example, at the integer fillings, right? You can scan, right? You can map out these energy levels associated with these integer quantum Hall states, and then you can go to these fraction quantum Hall state and map out the energy level again. You will see 3 times more energy levels compared to integer one. So that's another evidence of fractional charge excitation in the system. And the Hablon, right? Marty got it recognized last year, right? For these measurements. And the other way to do this is to measure the fractional statistics, right? This is this is another advance in the community, right? By doing these quantum Hall interferometers, right? For example, the progress is made by these Michael Manfred. They do these quantum Hall interferometry measurements in the gallium arsenide, and when you tune the anyon numbers in the system, they see these phase slips. And from there, they can infer the change of phase is about 2 pi over 3, corresponding to 1/3 charge. And recently, these quantum Hall interferometry has been adopted to the graphene communities. This is a beautiful result from Philip King's group at Harvard. It's a very interesting experiment. Basically, their instruments actually not perfect. If you do transport, you know that, especially at the dilution-free temperature, if you don't filter out your noise, actually there's a lot of microwave photon will go into your system. In this case, this microwave photon actually helped them to create these telegraph noise. And it turns out this telegraph noise is exactly the measurement of fractional statistics of this 1/3 state. Yeah. So it's a beautiful, I would say, the imperfect system gives you perfect results. Yeah. Okay, so I think Michael and got recognized last year, right, for these beautiful measurements of quantum Hall interferometers. But our sample, I would say, is not there yet, right? We have low mobilities, and it has difficult fabrication of the contacts, and we cannot do all these fancy measurements of either noise measurements or interferometry. I want to do it, but it's hard. But what we found is that actually we can also use light to do some of these measurements. At least we can probe the fractional charge. So that's the rest of my talk. What I show you is that we observe a new type of fractional charge complex we call fractional trions or anyon-trions. And what I show you is by doing spectroscopy measurements, we can actually determine the fractional charges from these fractional trion spectroscopies. So in case you don't have much optical background, I want to give you some basics of light and matter interactions. Right? I shine light to a semiconductors. I will create a electron and a hole pairs. And these electron hole pair can bond to each other through Coulomb interactions. So that's called neutral exciton. Neutral means it's a charge neutral, but it's a bound state. Then I can start to dope the systems, right? Imagine I dope a hole to the systems, and then in a dilute doping, what it means is the screening is still weak enough. Then these exciton can bind to extra carriers to form a charged exciton, so we can trions. Now here the trion formed by 1 electron and 2 holes. So trion, right, will have a lower energy compared to exciton because it's a binding state. And spectroscopically, we can tell them apart, right, by looking at their energies. So here I show the example of photoluminescence spectra of a molar MOT2. So the top spectra is from charged neutral exciton, and the bottom spectra is from a hole-doped trion state. You can see that the trion state, right, has a 20 millieV energy difference, right, compared to the charged neutral excitons. Okay, so that's how we tell. There's neutral exciton, there's trions. We can do a bit more measurements, right? For example, here now I show you the intensity plot of these photoluminescence measurements. Now the vertical axis is doping, horizontal is the energy of my photons, and the positive means electron dope, and negative means hole doped. So from this plot, you will see that the charge neutrality, we have a neutral exciton here with these little weak features. And I start to dope the system. Now I see that the negatively charged trions or positively charged trion appears. Okay? So that's another way, right? We know that the system is doped we have a neutral exciton, we have a charged exciton or trions. Now we go look at these twisted MOT2 bilayers. And I look at the trion luminescence again as function of a filling number, right, in these vertical axis. You will see that at these fractional transition state, right, the luminescence actually quench a little bit, right? We have 3/5 state, we have 2/3 state, and at the integer filling -1, we have see the same thing again. So this actually tells us that we actually have a simple optical readout of the fractional state. In fact, that's how we initially found this state, through optical measurements. Just give you a simple picture, right? Why trion luminescence actually is quenched at these fractional state. The simple argument is that the trion, right, is an exciton bound to a fractional charge. Okay, so it means you require the electron or hole population in the system. So whenever there's a incompressible state, the Fermi series actually gapped out. So the electron or hole population is decreased, right? So when you have a reduced population of charges, then there's a reduced population of trions. And this reduced population will just evident by these quenched luminescence, okay? So what we can do, right, experimentally, I can do a spectral integration of my luminescence intensity. For example, right, I can do integration over these spectral windows, then I plot the intensity as function of a filling number again at the particular magnetic field. And I can identify these dips, okay, correspond to these integer or fractional states. When I plot these data as function of a magnetic field, this will give me optically detected fan diagrams, right? I assume you know what the fan diagram is. Usually is done by transport, but we can also use optical method to do these fan diagram measurements. And with this fan diagram, we can identify several features, right? First of all, the integer feature -1, right? You see there's the line actually tilted, and it has a fraction filling 2/3 and -3/5. So we can extract the carrier densities correspond to these dips and plot it as function of magnetic field. Then we can overlay the strata slopes on top of these extracted densities. This gives us the assignment of chain numbers, right? We have a quantum anomalous cell at the 1 filling factor -1. Then we have these fraction quantum anomalous cell at the fraction fillings. That's how we actually initially determine we have the state in the system. Then we did the transport to confirm this state. But this, I want to just show you that we have a simple optical way to determine these states. Okay, now I have these states. I told you that I have trions, and they can be used as a probe of these FCI states. Now, one of the questions to ask is, well, when we tune the carrier density, say to these fractional state 2/3, right? And in the background, we have a trion state, and we have a lot of fractional charges. The question is whether these trions can talk to these fractional charge. For example, can they bond together to form a complex quasi-particles? If this can happen, then I can just read out these complex particles spectroscopically. I can read it out, and it can be used as an approach to measure the fractional charge. Okay, so that's what I'm going to talk to you for the rest of my talk. So in the community, because we know that the fractional quantum Hall has been there for 40 years, right? So the community have been thinking about almost, they've been thought about almost everything. So these fractional trions also been considered theoretically, and also a lot of group has measured it experimentally. And there's a lot of theory there. Here I just use one example, right? In this particular theory, they consider there's a whole gas layer, and with these 2D electron gas systems. But they show that if the separation of this whole gas to the 2D electron gas is smaller than the magnetic length, then the hole will just band to electron to form these neutral or charged excitons. So it means there's not a fractional charge. However, in the condition that if the separation, right, D is larger than 2 times of the magnetic length, then this hole can bind to Laughlin quasi-particles to form these fractional charged exciton or trion states, okay? So that's what theoretical predictions. And there's a lot of experiments being done in the community. Here I highlight one of the experiments. This is most close to what I'm going to show you in my talk, right? So this is the measurement this photoluminescence measurement of gallium arsenide samples. And we can focus on this panel first, right? This black curve is actually transform measurements. They measure these RXY, right, as function magnetic field. You can think of a tuning of the filling factor in the Landau levels. So this magnetic field corresponds to 1/3 of fillings, all right? And the bottom is a luminescence measurement. It's a color plot. So the vertical axis here is energy, horizontal again, right? It's a filling. So what they show is that when the plateau start to deviate away from this quantization, means the system, right? You start to have a mobile anion in the system. And they observe there's a sharp change of this energy of luminescence. Okay? Basically, a new feature appeared at the low energies. And this also emphasized by this middle plot, right? From top to the bottom, what they do is by tuning the filling factor by magnetic field. And at the at the plateau, near the edge of the quantization plateaus, there's an emergence of new peaks at the lower energies. So the paper actually combined with the theory calculation, they claim that this new feature is a fractionally charged trion state. Okay? Right? The evidence basically is that when you dope this fractional state, you inject mobile anion to the system, and they observe a new feature at the lower energies. And this new feature is attributed to this fractionally charged excitonic state. Okay. So keep this feature in mind. There are also other theory paper in the community, just appeared. This is the paper actually appeared last summer, July 22nd. It's from Fabian, Attach, etc. They consider these a different scenario. So you have a TMDs on top of a monolayer graphene, and they consider an interlayer exciton bind to a quasi-host inside a graphene fraction quantum house. So this is another example of anyon-trion excitations. Okay. So let me show you our experiment. Right. What we have here is I have these samples, which are kind of unique sample. Means in addition, I have a twisted monolayer on monolayer, when it's a twisted bilayer, right? I have a twisted monolayer on top of a naturally bilayer. So there's an interface formed here. So what we found is interface is interesting, can trap these fractional charge. So on the right-hand side is the luminescence plot from this interface. And if you're not familiar with this type of data, right, you probably cannot tell the difference. But let me just compare these data with a clean sample I just showed you. You probably see the difference, right? In addition to this main feature, which is luminescence from free trions, in this new sample, we actually have a replica on the low energy side, right? This replica has a narrower line width. That's the feature we observe. Then first, let me just take a line cut of this feature and look at the spectra. Here's a luminescence, right? Taking at the filling factor about 0.8. Now we see that I have a main free trion feature with line width about 1 millielectron volt, and then I also have a narrow feature sitting on the shoulder with line width about 200 micro EVs. And this narrow feature is, we know that, right? If in the community, we know this narrow feature actually is come from trapped excitonic states. Has been demonstrated in many different examples. These trap potential can be provided by defect impurities, can be provided by local strings, can also be provided by electric field. So in my case, actually, I don't know exactly the origin of the traps. It could be because at the interface. It could be due to the electric field, could be due to defects, could be due to strings, but it doesn't really matter for my case because I know there's a trap state, and I'm going to use this trap state to read out the fractional charge. So let me just first, right, we do a spatial mapping of these, trap states. Indeed, what we find out that these trap states actually appear at the interface. Okay, so this dashed line here indicates the interface between twisted bilayer to twisted monolayer on bilayers. Okay. Then I can do these fan diagram measurements of these fractional states, as I just showed you for these, right? So what we found is that indeed, right, we have a many, fractional states. Right, it's a Jain sequence. We have a 2/3, 3/5, 4/7, 4/9, 3/7, 2/5, etc. So there's a bunch of them. So these little trap states actually is a very good sensor of this fractional changeless state. Then the second is, if you look at these data, you will see that, for example, 2/3 filling, right? Let's see something going on inside. So if we just zoom in, focus on is trapped state. Okay, so the bright background is from free triangle. Now we don't worry about it. Let's just focus on these narrow features. So the first thing I want you to pay attention is that when I dope my system to 2/3 fillings, you will see there's a plateau feature. So this spectrum, what I show you here, the vertical axis actually is the energy in my triangle luminescence. Horizontal is my dopings. So basically, when I dope the system to these 2/3 fractional state, there's a plateau appears. If you're familiar with transport, you know, right? When you do transport, if it's a fraction quantum Hall, you will see a quantization plateau in the Hall conductance. But what I here it shows you is a plateau with the intense energies. So it means that I do have an incompressible state in the system because I enter into this 2/3 FCI state. Okay, so I can compare my transport, right? So what's really exciting is that when I start to dope this 2/3 state, right, just a little bit, go beyond the center of this plateau, there's a abrupt shift of this luminescence energy, and a new peak appears at the lower energies. Okay? So this new peak, now I'm going to call it fractional triumphs. And then as I keep dope the system, we'll enter into this anomalous Hall metal phase, right? Then you can see there's another change of this energy of the state, and the anomalous triumph appears a continuous dependence on the dopings. So this bright feature showed up at the doped FCI state, right? I call it a fractional triumph or anyon-trions. And I show you more evidence why we say that. Then we can also look at these 3/5 state again, right? When we dope these 3/5 state, you will see there's a little plateau in terms of energies. Then there's a little bright feature appears as we dope it, okay? All right, and this data can be observed in many different traps. So here are the two different examples, right? Let's focus on right one, For example, the 2/3 state, we see a little plateau feature with a bright feature when we dope it. And the 3/5, again, we have a little plateau feature. And I dope the 3/5 state, there's a bright feature shows up. Okay. So this little bright feature we call fractional charge the triumph state. So how do we know, right? There's many checks we've done. The first is I want to do these electric field dependence. And what you see that the zero electric field, right? Here's zero electric field. And vertical axis, the filling factor, I see this fraction triumph with this plateau feature. As I increase my electric field, you will see that the two states actually disappeared. So if I focus my filling just at the transition from these FCI triumph to a fractional triumph, and I plot it as function of a continuous tuning of the electric field, and the horizontal axis gets energy, you will see that, right, this fractional triumph has a similar electric field dependence to the FCI triumph, but disappear first before the FCI triumph disappears. So what it means is that the formation of this fractional triumph actually requires the protection of the FCI gap. Okay. We can also do these temperature dependence, right? You will see that the thermal excitations can kill these FCI triumphs or anyon triumph together. So this also shows that the correlation between these fractional charge triumph to these FCI state. And we can also do these Venn diagram measurements again, right? In the data, what I show you here is I do these spectral integrations of these features and plot as function magnetic field, these vertical axis. Now we can focus on these 2/3 filling, right? We see that there's a feature with a little, wider, broader, and there's a narrow feature. Both of them actually has the same straight slope 2/3. So the broad feature is from the FCI state, and this narrow feature actually from these anyon-trions. Okay. So all this shows that this new feature I show you, this narrow trap state, right, only appear at the doped FCI, I call fraction triumph, has these 2/3 topological features. The reason is important because this anyon-trion actually bound to a fractional charge, and this fractional charge only exists in the system in this 2/3 FCI state. So now I show you this evidence, right, is that when we dope this FCI state, when the mobile trions, I have a new state appears at the lower energies. So this is very much close to these, the example I show you, right, in the 2D electron gas system, right? And that shows evidence of this fraction charge trion state. But in realities, if I show this state to you, you might be convinced there's a state, but how do we know this really fractional charge? right? I know the state is 2/3. So what that means is the charge must be fractional, must be 1/3. But that's just a theoretical expectation, right? As an experimentalist, we need to prove the state is correspond to 1/3. So how do we know that? Well, there's one way to do it. We can look at the energy difference, right, between these FQAH trion and these anyon-trion. This energy difference corresponds to the binding energy of the state. So the binding energy means have a quasi-particle and then bind to these anyon-trion, bind to these trion, form these fractional charge bonds. And the binding energy of these 2/3 state is about 800 microeVs. Still, 800 microeV, doesn't tell me the state is fractional charge. So what we can do is then we compare the other fitting factor, which is 3/5. And from there, we can also get the binding energy of 3/5 state with about 500 microeVs. Now these two numbers will be meaningful, right? So what we did is we measure many different traps and compile all these data together. Now this blue dots represents the binding energy of these fraction trion of the 2/3 states, right? It's all around 800 microeV. And orange dots represent the binding energy of the 3/5 states. It's all around 500 microeV. And the green diamond represents the ratio of the binding energy of the 2/3 to 3/5 states. And you can see the green diamond actually scattered around these dashed line, which is a 5/3. That's a ratio of the fractional charge. So the take-home message is that what we found is that the binding energy of the 2/3 state to the 3/5 state is equivalent to the ratio of the fractional charge 1/3 to 1/5. So that's our strongest evidence that we can read out the fractional charge use this optical spectroscopy technique. So so that's implications. The implication is that by the binding of these anyon particle, right, the binding process doesn't really change the wave functions because we know the fractional charge is lofting wave function properties. If you change the wave function, there's no fractional charge. So what this shows that the binding potential cannot be too large, has to be weak. Okay, weak means doesn't perturb the wave functions, but it cannot be too small because when too small, then you cannot trap the state. Then we cannot see this. All right. So I will skip these slides. Maybe my time is up. Yeah. So this is I know Yale is the center of quantum computing, right? I want to just put these slides here, right? I think one day if we can realize these fault-tolerant quantum computations, use anyons. That's my vision, right? We can use anyon to do computations, and we can use these quantum dots to read out these informations to build these photonic internet, okay? And we know that the gap of these states actually can be tuned from these, close to milli-eV to a few hundred micro-eV. So what that means is that they actually can also in resonance with the superconducting qubits, right? So maybe one day we can build these hybrid anyon quantum computer and the quantum internet. With that, I'm going to summarize, right? This just a kind of a summary of the roadmap of these quantum Hall families, right? From these initial discovery of a quantum Hall to the fractional quantum Hall effect, and about a little bit over a decade ago, right? There's the realization of integer quantum anomalous Hall effect, and a couple of years ago, we finally got this fractional quantum anomalous Hall effect. And the excitement is here is that the system itself is highly tunable. So what that means is we can use it, right, to actually look for new states of matters, right? There's a couple examples. For example, right, we can go for these non-abelian anyons zero magnetic field. The second example, what I'm really excited about is look for superconductivities, but arising from these fractional charge excitations. Okay, so with that, I want to thank all my collaborators, my students who did this work, and also the funding agencies. And thank you for your attention.
Okay, thanks Xiaodong for the great talk. I think we are a bit tight on time, so we'll just take one or two quick questions, if there are any.
Thanks for the nice talk. I'm curious for the integer quantum anomalous Hall states. Do you see similar like trion the binding state between bond state between the trions and.
It's a trion, but it's integer binding, so it's just like normal trion.
So you do see these additional states, bond states, and compare the gap with.
There's no additional state. There's just normal trion state.
Just normal.
Okay, you will see a shift, but it's like normal trion state.
I see. So no like let's say 1 electron bound to 3.
No.
No.
That's
no
right.
this kind.
No. Yeah, that's one question.
Hi, thanks for that talk. Regarding this bound state, I'm just curious. I see that from the fan diagram that you showed, the bound state appears in the little bit epsilon hole-doped from the say negative 2/3 states. What breaks the particle hole symmetry? Like, why do we not see this like a bound state in the like negative epsilon doping?
Because the trap itself only binds positive charge. Right? It's a trap. The trap, can choose bind the negative charge or positive charge. So the trap itself here only bound the quasi-holes. So yeah, that's the simple answer.
And the source of the trap is just some defects, or
that's why I say I don't really know. But there can be defect, can be string, can be electric field. Yeah. We don't know the exact origin.
Okay, if no more questions, let's thank Xiaodong again.